In this section, we learn how to solve linear systems using systematic method, essentially some sort of recipe that will give us the solution to any linear system very easily once we know how to apply the steps of that recipe. And to understand how we are going to obtain the solution set, what we have here are augmented matrices obtained from linear systems, and they essentially will correspond to the last step essentially of our algorithm that will give us the solution set. So once we will have manipulated the equations of our solution set, we'll end up with matrices of that kind. Our first exercise is essentially going to consist in recovering the solution set from the equations that are related to those augmented matrices. So let's go through these four examples. So you have to understand that this is a matrix related to a linear system, but they don't have to be related to linear systems, matrices in general. They could stand on their own and be coming from some other application. But here I'm telling you that it's an augmented matrix, and that's the word that is important here. So augmented matrix tells you that it's related to a linear system. So maybe we could think that our variables are x, y, because in an augmented matrix, the last column will correspond to your constants, and the other columns will be coefficients related to your variables. So if you've got three columns, that means you've got two variables, because the last column includes the constants, and the first two, they include even though I wrote x, y, they include the coefficients, right, for those variables. So sometimes we will call that matrix here, that's a matrix, the matrix of coefficients. So let's write in A the corresponding equations. Okay, so I've got 1x plus 4y equals 1. I've got 0x plus 1y equals 2. Now 0x is going to be 0, right? Whatever x is. So usually we won't write that down. And 1y is just y. So I'll simply write y equals 2. The last equation reads 0x plus 0y equals 0. Now if you think about this, no matter what x and y are, the left-hand side is going to be 0, right? So this is just saying 0 is equal to 0, which we know is true, right? Everybody knows that 0 is 0. So the last equation really doesn't provide us any information whatsoever on what the solution set is. So any xy would satisfy the last equation, so it's useless. However, not every xy would satisfy the first two, so I've got to keep them. To recover my solution set, what I will do now is called a backward substitution. So I will move my way up, starting with the last equation and solving for each of the variables. Backward substitution. So you'll see what I mean by this. So we started with the last equation. So y is 2, right? So that means that if xy is a point in my solution set, that y coordinate is 2. Okay. And I move my way up. I look at the first equation now, and I solve for x, and I do what's called a substitute. So this is the backward substitution step. I replace the other variable that I found, which is y, by its value 2. And from this, I can recover the value of x. So it turns out here that x is also fixed to minus 7. So the solution set here has only 1 point. So it's minus 7, 2. Or sometimes you can write it x equals minus 7, y equals 2. So both are good. So we've got one solution here. And maybe you'll recall that for any linear system, the number of solutions can be either, well, no solution, one solution or infinitely many. Okay, so as soon as you've got two, you've got infinitely many. So here's a case where I only have one solution. So B, once again, maybe I could call my variables x and y. If I have too many variables, right, I'll start labeling them with x1, x2, x3, and so on. But here I just have two, so I like xy. So this says x plus 0y. Now remember, 0y is always 0, no matter what y is. So I could just write x equals 1 for my first equation, y equals 5 for my second equation. And it sounds like maybe the solution set is 1, 5, but hang on. Look at the last equation. It says 0x plus 0y. So that's just 0, right? No matter what x and y are, is equal to 1. And that's not good. 0 is never equal to 1. So no matter what values I assign to x and y, 0x plus 0y, which is what I have on this side here, so 0, is not going to be equal to 1. So I can't choose values for x and y that will satisfy this system. So this is impossible here. I cannot have 0 equal to 1. So there are no solutions here. Okay. C. So maybe before moving on, more of the story is as soon as you have a row that's almost, well, a row that's almost a row of zeros, where what I mean by that, all the coefficients for your variables are 0, but the last entry in that row, so the constant term, is non-zero, you will detect a linear system that has no solution. So here in C, maybe we could call the variables x, y, z. So we've got x plus y plus 2z. Notice how I draw my z. I put z with a bar, otherwise it kind of looks like a 2, right? Especially I've got a 2 in front of it. So I'm doing two things here. I'm writing my 2 like this, and my z with a little bar. So there's no confusion whatsoever between the two symbols. So I recommend that you do that as well. So that's equal to 1, right? The second equation just says z is 3. And the last equation is like in part A. We've got 0 equals 0. So that's giving us no information. So even though we've got technically 3 equations here, the only the first 2 are relevant. So it's really a system with 3 equations and 2 equations and 3 unknowns in disguise. Okay. So let's try to recover the solution set once again by doing what I call the backward substitution. How do we do that? We start with the last variable. Z is 3. Okay, so I know here Z is going to be equal to 3. Now after that, I've got X and Y here. I've got some freedom, right? In the sense that I could say, well, Y is 1 and then solve for X to make it all equal to eventually 1 here. So if I do this, you see I would get 1 plus 6, 7. So X would have to be minus 7 for it to work. If I assign a value of 0 to Y, well, in that case, X would be minus 6, and so on. Okay, so essentially, by assigning a value to Y, I can solve for X and get a point in the solution set. So since there are infinitely many possible values I can assign to Y, I will say, oh, Y is going to be my T, my parameter T. Let Y equals T, where T is my favorite real number. Then X is, let's solve the first equation for X. X is 1 minus Y minus 2Z. So that's 1 minus T minus 6. So as soon as I assign a value to Y, X is now fixed. This is what I had observed here when I was assigning values to Y. If I assign a value of 0 to Y, automatically X is going to be fixed. It's going to be minus 6. If I assign a value of minus 1, in that case, X is minus 5. Okay, so as soon as I fix the value of y, x is fixed. So that's why my solution set has only one parameter, 1 degree of freedom, essentially. So the solution set is, what is it? Well, I can write it like that. X, Y, Z is 1 minus t minus 6. Y is t, and Z is 3, like that. So that's then where t is my favorite neural number. So that's kind of our answer. And let's take a deeper look at this. I could split it so that well, actually, you know what? I could have done something slightly better. You realize I have two constants here that maybe I can regroup. I didn't do that. I should have done it here, actually. Minus 5 minus t. So minus 5 minus t, t and 3. That's actually better. T is a real number, so actually this should be my answer here. Like that. And what I was about to do is split it up. You see, I could look at just the constant part and the part that contains t. Like that. And now that you've done chapter 3, what kind of object is that? What object is represented by that set? Well, that's an object of the form P0 plus TV. Right? So what is that? It's a point plus some multiple of a vector. So what kind of object does that describe? Right? That's a line, right? Passing through our point P0, which is minus 5, 0, 3, and pointing in the direction, or parallel to the line, parallel to the vector, pointing in the direction, or you can write parallel to the vector of V, which is minus 1, 1, 0. So that's because essentially what we have here, if I look here, I've got two non-parallel planes. They're not parallel because for parallel planes I need to have parallel normal vectors. And if you look at the normal vectors, which are 1, 1, 2 and 0, 0, 1, they are not proportional, so therefore they're not parallel, and my planes are not parallel. So I've got two non-parallel planes, and when you've got two non-parallel planes, that means that these planes will intersect. My drawing's terrible. They will intersect these planes, like so. Okay, and they will intersect along, so of course I only drew part of those planes, right? And they will intersect along, what did I do here? Along a line. Okay, along this line, for example. So that's why we're finding a line for the solution set. So having done chapter 3 gives us an advantage in understanding what our solution set represent. Okay, let's go back and take a look at D now. D is a big system, right? It has x1, x2, x3, x4, has 5 variables, right? What would be the solution set? Technically, I'm going to do a backward substitution, but look, I'm going to start with the last equation, and how does that read? It reads just like this one here. It reads 0, right? So this is 0x1, 0 plus 0x2 plus 0x3 all the way to 0x5, no matter what x1, x2, x3, x4, x5 are. This part is going to be 0. 0 equals 1. So that's never going to be true. So maybe let's write D here. The last equation is 0 equals 1, which is impossible. So in this case, there are no solutions. There are no solutions. So all these linear systems, the matrix was such that I could easily do my backward substitution. So we are going to be interested in describing what's so particular about these matrices that make my backward substitutions possible. And we're going to call those matrices matrices that are in row echelon form. So what I'm about to write down now are the conditions that make the backward substitution possible, that make a matrix in row echelon form. I wrote what I just said, so the previous linear systems were easy to solve since we could do a backward substitution. And the question is, what kind of matrices would be good for our backward substitution? And this calls for a definition. So this is where mathematicians create objects that are good for a purpose. So here we are going to define matrices that are essentially generalizing the matrices we have seen in A, B, C, D. So those matrices were good for backward substitution. Let's see what's good about them. So we're going to define a matrix in row echelon form in the following way. So the definition is for what row echelon form means. So a matrix will be in that form if rows of zeros are at the bottom. Now I've put an example here to illustrate what a matrix in row echelon form might be. I just realized that maybe I should add a row just to show you the first condition. So let me do that. Here we go. So as you can see, this matrix has two rows of zeros at the bottom. They can't be at the top, or they have to be stacked at the bottom of the matrix if we want it to be in row echelon form. So that's property number one. Property number two, in a non-zero row, the first entry that is not a zero is a 1. So the rows that are non-zero rows, are the first 4. Okay, because there's an entry in there that's a non-zero. So what entry is a non-zero in the first row? It's this one. What entry is a non-zero? The first non-zero, it's this one in the second row. It's, this one I should slightly change it to a 4, to a 1, if I want my definition to work. So 1 here and 1 there. So in this matrix, the first non-zero entry in that row is a 1. So property number 2 is satisfied. And number 3, in any two successive non-zero rows, the leading one in the lower row occurs farther to the right than the one in the upper row. That's kind of hard to digest, but look what I wrote in the brackets. It's easier to remember this way. Leading ones are along a diagonal. I wrote diagonal in, it's not it's not an exact diagonal. So you see here, if I've got a leading one, the next one has to be a little more to the right. So you look here, oh yes, it is. See, because I can go along a diagonal like that. And after that, I can go like this and reach the other leading one. So it's a little more to the right again, and this one a little more to the right. So it's not an exact diagonal, but they occur just kind of diagonally. So if you have got a leading one here, for example, that we wouldn't have, if you had a 1 like right there, then in that case you wouldn't have property 3 being satisfied. But here it's not the case. So if we quickly go back and look at our matrices in A, B, C, D, look at rows of zeros are at the bottom right there. Ones occur diagonally, and the first non-zero entry in a non-zero row is a 1. So that's in row echelon form. Here, I just need to look at the ones, they occur diagonally. So essentially, property, the last two are satisfied if the ones occurred sort of diagonally, and below them you've got zeros. You see here below them I've got zeros, so that works. Here I've got my 1, and that's it. I've got a last row that's a row of zeros, and below my leading ones are zeros, so that's in row echelon form. The last one isn't as per se in row echelon form because of that little 4 there, but if I change this, I can actually do that. If I changed the 4 to a 1, now it is. It's basically the almost the example I gave you below, except that you don't have those extra 2 rows of zeros stacked at the bottom. So those are all matrices in row echelon form.